Okay, last week we had started with this problem, but suddenly it was interrupted, so let us finish it properly. I think it was when we arrived at this compound Z that it was interrupted. Let's read again from the beginning to remind us what it's all about. Three alkenes, X, Y, and Z, have the same molecular formula. Describe what is seen when aqueous bromine is added to X. Okay, X is the first one, it's an alkene. When bromine is added to an alkene, because it is an unsaturated hydrocarbon, the color of the bromine solution, which is orange-brown, changes to colorless, which means that it reacts with the alkene. It's an electrophilic addition, if you remember. And actually, this is the test for an unsaturated hydrocarbon. If we add the solutions to be tested into bromine water and it changes color, means that there was a reaction, which means that this hydrocarbon was unsaturated. Now, the next question says, X, Y, and Z are reacted separately with hot concentrated acidified manganate ions, hot and concentrated. All right, until no further reaction occurs. The carbon-containing products are shown in the table. You know, when these compounds, hydrocarbons, react with acidified manganate, which is a very strong oxidizing agent, hot and concentrated, we know that they are talking about oxidation reactions, oxidation of alkenes, which are very often these type of reactions are coming in the exams, in exam questions. I see them, the oxidation of alkenes. Okay, but remember now, if this acidified manganate solution is hot and concentrated, there are specific products that may be produced depending on the type of the alkene that we had, and there are these three types. We discussed it last week, but quickly let's see them again. These three types of alkenes will produce different products with if we react them with hot and concentrated manganate ions solution. And how do we know is that, you see, if one of the carbons from the double bond is connected to two hydrogens, then the product of this from this part of the molecule will be carbon dioxide. If one is hydrogen and the other is some other type of alkene, the product will be eventually carboxylic acid. First is an aldehyde, but this is further oxidized and produces some carboxylic acid. And if both of these, both of the constituents connected to this carbon is both some types of alkyl groups, then the product will be a ketone. So in this case now, they give us the products here in the table. They give us the products, carbon-containing products of these alkenes. And we see here we have a carbon dioxide and a ketone. This is a ketone. There's we can see the carbonyl group there. The other compound Y, we see produces again carbon dioxide and an acid, a carboxylic acid. You see this, it's a carboxylic acid, the functional group of the carboxylic acid. And so is compound Z, but here it's only acid that is produced, not carbon dioxide. So from these products, we can figure out what were the X, Y, and Z. Now, the first one, the compound X. Now, draw the structures of X, Y, and Z. Let me the structural formula. I think we had done this before the interruption. look at this. Since one of the products is carbon dioxide, means that one of the carbons in the original alkene was connected to two hydrogens. But the other product now is a ketone. And if we look here again, if we have this whole picture here, look at this, the ketone product comes from a carbon which is connected to two alkyl groups here. So obviously the other carbon, in our case here, the other carbon, I'm talking about X, the other carbon was connected to two alkyl groups. Which groups are these? Here they are, the methyl group. So here is the one, the compound X. If we write it in this form, the structural formula of the molecule, this is what we are going to get. The second, the Y you see comes again from a carbon, the product is a carbon dioxide again, which means again one of the carbons of the double bond is connected to two hydrogens. So this carbon dioxide comes from this part, and the other part is it's an acid, a carboxylic acid, which means carboxylic acid is the product from a carbon which is connected with one hydrogen and one alkyl group. First, it gives an aldehyde, and then the aldehyde oxidizes further to give us an acid. So here we are given the acid straight away. So we know that the other carbon here is connected to one hydrogen, and the other will be this this part here, this alkyl group. Here we are. And what is this group? Is all this this alkyl group. So that is why if we write it in this form, the structural formula of the molecule will be of this type. Right, so this is compound Y. And find why I could write all these shapes in here. Anyway, the Z finally, the compound Z is giving us just acid, some carboxylic acid. Two of these molecules will be produced, and when we have the production of a carboxylic acid, obviously we are in this type of oxidation where we have an alkene with both carbons must be connected, one with a hydrogen, the other with some alkyl group. So that is why here is the structural formula of this compound Z, which is, if we were to write it in this form, that would be, we said, one hydrogen, and the other part would be this methyl in this case. So one alkyl group, one hydrogen for both carbons, because we have only acid, carboxylic acid produced here. Okay, so deduce the molecular formula of X, Y, and Z. Well, remember that at the beginning they told us they all have the same molecular formula. Obviously the same molecular formula, all of them. I mean, if we're going to write the same molecular formula for each one of them. So let's take one and let's find out how many carbons and how many hydrogens we have and how many anything else. Well, if we look at this one, for example, how many carbons we have? 1, 2, 3, 4 carbons. And how many hydrogens this should be? If we add them together, we get 8 hydrogens. And we can see that this is actually of the type N carbons and 2 N hydrogens, because these are alkenes. So this is the molecular formula for all of them. All of them consist of 4 carbons and 8 hydrogens. Okay, is there any question here? You can let me know, or else we can. I gathered together problems that concern alkenes mostly, because with alkenes, apart from the oxidation of alkenes, which you need to know that very well, all the different products of the alkenes when they are oxidized, when the oxidizing agent is the manganate ion, acidified manganate ions, but be careful of the distinction between hot and concentrated, which gives all this these three types of products. If the manganate ions are hot and concentrated, in a hot and concentrated solution, or unless, because the other option is that the acidified manganate ions belong to a dilute solution at room temperature, and then the product is very different. It's a diol, if you remember. It's diol, which means it has two of these hydroxy groups in the product, but we're going to meet such things as well again. Now, let us see another problem from another exam paper, again with some alkene, but it's actually, let's see this problem here. What is this from? Where does it come from? Also from this year. It's a very recent paper. All right. So the structure of compound Y is shown. So this is the structure of compound Y. Give the systematic name of Y. Okay, we have 3 carbons here. Let's count them from the first one, but closer to the double bond. So let's say 1, 2, 3. So obviously this will be, there's a chlorine atom there. So that will be 3 chloro. Now 3 carbons is propane, but because of the double bond, it's a propene. Okay, so prop 1 in to show the position of the double bond. 3 chloro prop 1 in. Okay, so that is the easy part. Now, predict the values of the bond angles A and B shown in the diagram. Yeah, the bond angles actually. There is a chapter in the book about the organic molecules, bonds in organic molecules, and it's it's on page, which page is that? Page 193 and 194 in the book. Anyway, if we take this section, this first carbon first, where we have to decide on how many degrees is this angle A. You see this carbon, it's actually, it's connected to, it forms 4 covalent bonds. And which means that it's, remember that the structure of this carbon is like, forms a tetrahedral kind of structure. Tetrahedral structure, this, for example, could be the hydrogen, this could be the chlorine, this could be, let's, you remember this notation with the 3D notation of this tetrahedral structure, and these are supposed to be all that part here connected to this carbon. We're talking about carbon number 3 here, and because it's a tetrahedral structure, the angles of the typical angles of the tetrahedral structure are 109.5 degrees. So any of these angles here involved in this 3D tetrahedral structure will be 109.5 degrees. So it's kind of standard. So that is, they just want to see if you know it. So you see every little detail, you need to know it. Now, the angle B, now the other angle B. Now this angle is part of a double bond here. We have this carbon connected here to 2 hydrogens, and on the other side is connected to another hydrogen, this one, and some, and some other alkyl group. So I hope you understand that this is the same item like here, just I have written it in a different form to see the two carbons of the double bond. Why now? Because when we see a double bond here between two carbons, this kind of structure here, this molecule is actually a flat, it's a planar molecule. It does not turn, it's a rigid kind of molecule, which means that these angles between this hydrogen and this double bond, this angle here and this angle here and this angle here, are all the same, and they are 120 degrees, all of them. So this angle B that they are looking for, the one that they're asking for, is 120 degrees, and this is also 120 degrees despite my ugly drawing. All these angles here are 120 degrees. So our answer here for B is 120 degrees. It's also a standard, in other words. All right. Now, next question. When Y reacts with cold dilute acidified manganate ions, there we have the cold and dilute, the other type of oxidation of alkenes from the previous one. In this time, the acidified manganate ions, the solution of this acidified manganate ions is cold and dilute. The solution is cold and dilute. So remember last time we had the hot and concentrated, and we had all these options here of products. Now, because that was same acidified manganate ions, but hot and concentrated. Now we have the same thing, acidified manganate ions, but the solution is cold and dilute. When they say cold, they mean like room temperature. So the product here is very different. It's a diol, we said, which means we have two hydroxy groups, and they give us this is the product. The compound Z is produced here. We have the product, and you see the two hydroxy groups. So when Y react with so and so, this is the product. State the molecular formula of Z. The molecular formula, in other words, we have to say how many carbons and how many hydrogens and chlorine and oxygens. Okay, how many carbons do we have here? We have 1, 2, 3. So 3 carbons. Hydrogens, now how many? Obviously, if each carbon here carbons, this is skeletal formula. Each carbon forms 4 covalent bonds. So here is 1 and another 1, 2. So there are another 2 hydrogens here connected with this, isn't it? 2 hydrogens from this one and another one from connected to this carbon. 1 plus 2, 3, 4, 5, another 2, 6, 5, what? Yeah, 6, 7. So there are 7 hydrogens altogether. And chlorine, we have 1 chlorine, and oxygens, we have 2 oxygens. So this is the molecular formula of this compound Z, right? Okay. So name the type of reaction occurring when Y is converted to Z. When Y, the initial compound, is converted to Z, what type of reaction was that? Well, obviously, this was an oxidation reaction. Look at this. It reacted with acidified manganate ions in a solution of acidified manganate ions. Remember, manganate is a very strong oxidizing agent. So this is an oxidation reaction. So this is an oxidation reaction. Now, the last question here. Alcohols can be classified as primary, secondary, or tertiary. Identify with a tick the alcohol groups present in compound Z. This is the compound Z. We have 2 hydroxy groups here, obviously. So the the one at the end is the primary. So we tick the primary, and we have another hydroxy group which is connected to this carbon here, and this is a secondary alcohol group. Okay, so these are the two ticks. Now this question in this exam, yeah, the rest is not, does not concern alkenes. So let us go to another problem from another past paper, which we have seen before, but let us do it properly, because when we have alkenes, because of the double bond, it's very, very common to ask about isomers. And this will be stereoisomers. Hold it, I'm using my things here, my paperwork. Yeah. So let us see something with isomers to remind ourselves stereoisomers, which it's this example here. It's from 2016. Yeah. In each section, okay, of this question, an organic compound is shown. Okay, here's the organic compound. For each compound, give its name and answer the questions about it. So here's the organic compound, the name of this organic compound. Okay. 1, 2, 3, lot of this. 4, 5, 6. Let's see. Let's do it in this form so that it's easier for us. And then on the other side, we have hydrogen and all that. And another carbon, and another carbon. Okay, 3, 2, carbon. All this, why this pen doesn't write properly? Sorry, all these are carbons. This is this methyl group here. This is another hydrogen, this is a hydrogen, and these are all hydrogens. Okay. So 1, 2, 3, 4, 5, 6 carbons in a chain. So obviously this type comes from an hexane somehow, but because of the double bond, it's an hexene. All right. So the side which is closer to the double bond is where we start counting. 1, 2, 3, 4, 5, 6. So obviously this is, we have a constituent here, this methyl, which is at carbon number 4, right? So this would be 4 methyl X2 in, because 2 is a location of a double bond. It's at carbon number 2, eh? And it's an hexene because of a double bond. Here's the hex, the 4 methyl. So 4 methyl X2 in. That is the name of this hydrocarbon. This compound shows stereoisomerism. Okay. Defines stereoisomerism is it's molecules that have the same structural formula, same structural formula. Because the stereoisomerism, so they have the same structural formula. Obviously, the molecular formula is also the same, eh? But the atoms, so the groups are arranged differently. So what with different arrangement of groups, with different arrangement of groups, functional groups, constituents or whatever, in space, eh? Obviously in space, since it's stereo space. Different arrangement in space. That is why it's called stereoisomerism. Okay, and remember that there are two types of stereoisomerism: is the cis trans, or It can also be optical isomerism, and there's also this optical isomerism, optical one. Cis trans and optical. These are the two types of stereoisomerism. You know, when you see optical isomerism is usually when we have a chiral carbon. I hope you remember what a chiral carbon is. And so let us see now here. We have all that. Here is the double bond. And it helps if we write, for us to see the isomers, it helps if we write the alkene in this form. So if we write it in this form, what is there? The one is a hydrogen, the other one is this group here. It's methyl, it's a methyl group, like that. And on the other side, what do we have? We have, on this carbon, we have one hydrogen and all of that. So we have one is the hydrogen, the other one is all this, let's call it R. It's some kind of alkyl group with all of that. Isn't it? All right. So, hold it. Do I have it right? See? Where did I put my thing there? Yeah. Let me do something, because for us later on to see the chiral carbon, instead of writing all that as an R, I'll write it like this. This carbon here is this carbon here, which is connected with a methyl here, and the other part is all that, which is all that. I hope you see that this carbon here with the bold carbon, it's actually this carbon here, right? Don't confuse it with the one carbon next to it, which is carbon of the double bond. Yeah, now look at this. If we see it this way, we can see that, first of all, remember, because of the double bond, this molecule here, this part here is a flat molecule, which means that if all this contraption here, this is, instead of at the bottom, is put on the top, we are talking about a different isomer. So instead of, if this hydrogen was at the bottom and this was at the top, you see, these two now are not the same. They are isomers. These two are isomers. So so we have two isomers, a cis and a trans actually, in this case, because of the position of all this constituent here. And we also have two optical isomers in addition to those two. Why? Because this funny carbon here, this carbon, if you notice carefully, it's actually a chiral carbon. It's a chiral center. It's a chiral center. This carbon is called a chiral center. Why? If you remember, chiral center is a carbon that is all this, it's connected to 4 different groups. And what are the 4 different groups? Here, this is one of is connected to this alkyl group, this one here. The other is connected just to a methyl group, and another carbon, 1, 2, 3, I forgot, it's hydrogen, what, 1, 2, 3, there's also hydrogen here, sorry. The other one is the hydrogen, this hydrogen, which I forgot to write. And the other one is all that part here that contains the double bond, let's call it R. So you see, each each of these four um, uh, bonds that the carbon can form is something very different. Each of these substituent groups is different. Therefore, this carbon is chiral. It's a chiral carbon. And whenever we have a chiral carbon, it can form two optical isomers because if remember that these four bonds actually form a tetrahedral kind of structure. The one will be, how do we represent the tetrahedral structure in 3D? It's something like that, terrible drawing. So the one could be, for example, this constituent, which is up there. The other could be the hydrogen. This could be this methyl group. This could be this R, which is all that. But this, its optical isomer would be, as long as we interchange any of these sorry, what am I saying here? Okay. And so these two, in other words, are also isomers. They're not the same thing. It's like like a mirror image between our two hands. They look the same, but they're not. They cannot overlap if we put them one on top of the other. So we have two cis-trans isomers and two optical isomers, and therefore altogether we have four stereoisomers. And oh dear, we need to stop now again. So guys, again, next week we can continue maybe with halogen alkanes or alcohols and other functional groups. Okay.